Okay, the trapezoidal rule. So we're going to approximate a definite integral using the trapezoidal rule. So you can use the fundamental theorem of calculus, hashtag FTC, to find the exact value of the area under a curve. But there are a couple of situations where it's impossible to find the exact value. One of them is if your function does not have an antiderivative, and the other one is if your function is determined through experiment with the collected data. In which case you need to find another way to approximate the area under the curve. Well, Riemann sums requires us to use rectangles to get an approximate area, but maybe rectangles are not the way to go. Maybe we should use another shape like a trapezoid. So first, reminder about the area of a trapezoid formula and the definition. Some people and some textbooks would argue that a trapezoid just has one pair of parallel sides, or at least one, or exactly one. It really depends on your textbook, but we're going to go with the fact that we have one pair of parallel sides, and of course you have the height there is the distance between the two bases. Now, our trapezoids today are going to be right trapezoids, and they're going to be, as you can describe, maybe sitting on its side. So the bases are always going to be the sides that are parallel to each other, and then the height is going to be this horizontal distance that's between the two bases, and that's going to create a right angle to each base. And then, of course, this is the formula for area of a trapezoid. So 1/2 times the height times the sum of the bases. Let's start with this one. Here I have a function, just a random function, just drawn here in red. And I'm going to consider trying to find the area under the curve from 1 to 5 using 4 trapezoids. You can see that I've already drawn them in. So from 1 to 5, and then using 4 trapezoids. So it was pretty easy to determine that the distance here, the dx, if you will, has to be 1. And that represents the height of the trapezoid. We're going to take little baby steps here. Something that you could do here is you can sort of organize your information to a table. So we know we're going to have, I'm going to make a little column for each trapezoid, and then we'll talk about the area of each of them. So we'll have the first trapezoid, the second trapezoid, the third trapezoid, and you guessed it, the fourth trapezoid. All right, now let's consider the first trapezoid over here. I'm going to shade it in with this color purple. And let's zoom in a little bit as well. So for this first trapezoid, over here on the left, we're going to call that your base 1, and over there on the right is your base 2. And of course, your height of that trapezoid, remember this is a right trapezoid that's sitting on its side, the height is that distance, that horizontal distance between base 1 and base 2. So a couple of things. The height, hopefully you agree that the height of each trapezoid is 1. So when we're doing the area, for trapezoid number 1, it's going to be 1/2 times the height, which is 1, and then base 1 will be whatever f of 1 is. Let me explore that a little bit. So here's 1 right here, and this distance would be whatever the output is for that function. So if I plug 1 into my function, here's my function is labeled right here. If I plug 1 into that, that's going to give me that distance right there. So remember, this point right here would be the point 1 comma whatever f of 1 is. And then similarly, this point right here, which represents this vertical distance there, that would have coordinates 2 comma f of 2. And then this coordinate right here would be 3 comma f of 3. And this one would be 4 comma f of 4, and so on. Back to trapezoid number 1, it's going to be 1/2 times the height, which is 1, times f1 plus f of 2, f of 1 plus f of 2. So the second trapezoid, I'll do this one in green, the second trapezoid there, here's something that's different. Base 1 is on the left and base 2 is on the right. What was base 2 for the first trapezoid is now base 1 for the second trapezoid. So this would be 1/2 times the height, just using the formula for area of a trapezoid, times the sum of the bases. So base 1, b sub 1, that's going to be equal to f of 2. And then base 2 there, that vertical distance is going to be equal to f of 3, because that point is at 3 comma f of 3. So f of 3. And let's do the next one. So trapezoid number 3, shaded there in blue, and you can probably figure out that base number 1 on the left is going to be what was base number 2 for the second trapezoid, and of course base 2 in the third trapezoid is there on the right. So then we're looking at 1/2 times 1 times f of 3 plus f of 4. And the final one, you can figure that out, is going to be 1 times f of 4 plus f of 5, like so. Do you see how in each of these expressions, so we would add all these up, right? Add up these 4 expressions, and that's going to give us an approximated area under this curve from 1 to 5? Well, if you have the same common factor, right, we can factor that out, right? We can say that the area is equal to 1/2 times 1. So I'm factoring that out. And then I'm looking at the sum of f of 1 plus, check this out, I've got f of 2 and another f of 2. So that's 2 f of 2s. 2 f of 2 plus, here's f of 3, here's another f of 3. So I have 2 f of 3s plus, you guessed it, here's an f of 4, here's another f of 4. 2 f of 4. But there's only one f of 5. So take a look at this pattern here. Because the base number 1 on the left, where your lower boundary is x equals 1, that's only going to be one of your bases of your trapezoids. Same with the upper boundary, where x equals 5. That's only going to be one base of one trapezoid. But all of the other vertical divisions here, where you have your divisions, those are all going to occur twice because this is base 2 on the one trapezoid and base 1 on the other trapezoid. So all the ones in the middle are always going to occur twice, but the lower bound and the upper bound is only going to be once. So let's consider the same function, except maybe now we want to find it with 8 trapezoids, which of course is going to be even more accurate than only using 4 trapezoids. So my lower boundary is 1, my upper boundary is 5, and I needed 8 equal trapezoids. You can see I've already cut it up. So the height of each trapezoid in this case is going to be equal to 1/2. In this situation, when we're trying to find the area, it's going to be 1/2 because of the formula for height for area of a trapezoid times 1/2. That's your height of the trapezoid. And then you have the sums of all of the bases. We're going to have 1 f of 1. We're going to have 2 f of 1.5. We're going to have 2 f of 2. I'm going to run out of space here, etc., plus 1 f of 5. So again, all of these vertical distances here, these are all going to occur twice because they are the base 1 on the one trapezoid and base 2 on the other trapezoid. But your lower bound f of 1 and your upper bound f of 5, that's only going to occur once in each sum. So this leads us to something that could be considered a bit more of a formal trapezoidal rule. So it's a formula if you'd like. Personally, I would not memorize the formula if you recognize the pattern. Now, there are, of course, if you take AP calculus, there will be problems where the trapezoids won't have equal heights, in which case you might have to do a little bit more like working out instead of just following a pattern. So we have the integral of f dx is 1/2, and then that height of that trapezoid is b minus a over n. You'll recognize that from the Riemann sums. That would be the width of the rectangles. We just have our trapezoids on their side. That's why it's the height. And then we can call that delta x or dx. It's your change in your x going across each of your trapezoids. And then you've got f of x sub 0, 2 times f of x sub 1, 2 times f of x sub 2, but then just 1 f of x sub n. And so the 1/2 times the b minus a over n can be simplified to be like that, what I have in yellow. So you can write that down if you'd like. Let's have a look at number 1. We're going to use the trapezoidal rule to approximate the definite integral from 0 to 4 of x squared dx using 4 subintervals. I'm going to draw a sketch of my graph. There's my sketch. X squared is just a parabola whose vertex is on the origin, and I only drew this portion of the parabola because I am not interested in what's going on over here to the left. I'm only interested in what's going on between 0 and 4. So 0 would be, of course, over here. There's 0. And then 4 we could put over here. And we're using 4 subintervals, so that will be easy. Each interval will be 1 unit wide. So let's label that. So the delta x in this case, or the height of each trapezoid, remember that's b minus a over n. I mean, we kind of already figured it out in our heads, right? That's going to be 4 minus 0 divided by your 4 subintervals. So that's going to be equal to 1. But we figured that out in our head because we knew we needed 4 subintervals going from 0 to 4. So each interval had to be 1 unit wide. So now putting that into the formula, we're going to have the area equals 1/2, the 1/2 from the area of a trapezoid formula, times 1 times the sum of all those bases. So that's going to be 1 f of 0 plus 2 f of 1, 2 times f of 1, plus 2 times f of 2, plus 2 times f of 3, plus 1 f of 4. Okay, so 1/2 times 1, of course, is a half. F of 0, so your function, remember your function is just y equals x squared. So to find f of 0, you're just going to take 0 and plug it into your function. So that, of course, is going to be 0. plus 2 times f of 1, so take 1, plug it into your function. 1 squared is 1, plus 2 times f of 2, so that's going to be 4, plus 2 times f of 3, which is 9, plus f of 4, which is 16. And if you work all that out, you're going to get 22. So your area, technically you really should put approximation signs here, because the area is not exactly that. The area is approximately 22 square units. Let's take a look at number 2. This time I gave you the graph of the function here. It's 9 minus x squared, it's another parabola, and we're going from 1 to 3. And again, here it says when n equals 4, so there's going to be 4 subintervals. So I'm going to divide up let's draw in the lower boundary here, is at x equals 1. The upper boundary here at x equals 3. 4 subintervals, it's already labeled very nicely for me, so I'm going to have a division there and there and there. And if you'd like, you can draw in the tops of your trapezoids here. You'll notice that this one over here, this is technically not a trapezoid, it's a triangle, but the theory still works because you could say that the base 2 on this particular, quote, trapezoid would be, I have a height of 0. But here you can see the trapezoid, there's one base, and there's the angular section, and of course that would be the height of the trapezoid. Okay, so the delta x, that's going to be b minus a over n. So this is 3 minus 1 over 4, 2 over 4, so that's a half, which fit with our diagram here, where each interval here was just a half of a unit wide. So our area is going to be 1/2. You'll notice I'm not really using the trapezoidal formula that I had over here. I just think about it as the area is 1/2 times a height times base 1 plus base 2. That's really all I'm using, looking at the pattern. So I got 1/2, that's from the formula of the trapezoid, and then times a half, which is the height of each trapezoid, and then the sums of the bases. So I'm going to have 1f of 1, I'm going to have 2f of 1.5, I'm going to have 2f of 2, 2f of 2.5, and then 1f of 3, which, spoiler, is going to be 0. Should not be a spoiler because you can see it right there in the graph. Let's work this out a little bit here. So that's 1/4 times f of 1. Here's your function right here. Let me write that down. Here's your function here. F of x equals 9 minus x squared. So f of 1, plug that in, you're going to get 8. Plus 2 times f of 1.5, that's going to work out to be 27/4. When you take 1.5 and plug it into your function there, plus 2 times f of 2, which is going to be 5, plus 2 times f of 2.5, which is going to be 11/4. And I already you already knew that f of 3 is 0. And when you work that out, you're going to get about 9.25 or 9 1/4. Change that to approximate. So 9.25 square units is approximately the area under the curve from 1 to 3. One more example. This time, we're using n equals 4. I'm getting a little repetitive here. And we got some crazy function here, e to the x squared. We're going to go from 0 to 2. I would recommend that you graph this. Let's say this is a calculator question. So you're going to graph this on your coordinate plane. And you're going to end up getting a curve that looks a bit like that. And we're going to go from 0 to 2. Let's say that 2 is over here. And of course, 0 is over there. And we're going to be using 4 intervals. We're looking at there being half a unit wide. So a half, 1, and then 1.5 or 3 halves. Delta x, as we see from the diagram, is equal to a half. So we're going to have your area is approximately 1/2 times 1/2, and then times 1f of 0 plus 2f of a half plus 2f of 1 plus 2f of 3 halves. I'm going to run out of space. All right, I changed it around. And then plus 1f of 2. So that's going to be approximately 1/4. And this time I've got decimals. I went to 3 decimal places. So f of 0, well, that turned out to be 1 plus 2 times 1.284 plus 2 times 2.718. You'll recognize that as e plus 2 times 9.488 plus 54.598. When you add that up, you're going to get approximately 20.645 square units is the approximate area under this curve using the trapezoidal rule. And that's it. Hope you enjoyed it.